Hey guys, and welcome back to Quantic Academy. Sorry for the long delay since the last video. I was a bit busy, but today we're gonna talk about part 3 of the particle accelerator series, and today is going to be on particle detectors. Okay, so now how do we detect these particles? So now these particles usually have high energy because we accelerated them. So they have high energy. Now if you have a high energy particle, and you have an atom, for example, okay, let's just represent this as an atom, then it can actually knock the electron off, okay? It can provide enough energy to the electron for it to leave the entire atom. It can literally repel it out of the atom. So you can get, so if you have high energy particles, it can ionize atoms, and that leads to electrons and ions. Okay, so now you got free charge, so this charge can flow and you can detect this charge. Now if you detect this charge, that means you have detected the high energy particle, since that was what caused this charge. Okay, so how do we detect this charge? Well, we can use something called scintillation. Now scintillation is when a high energy charge, like an electron for example, hits a fluorescent material. Okay, so this fluorescent material is called that because when a high energy particle or a charged particle hits this fluorescent material, we get light, we get a flash of light. And so if we fire these high energy charged particles at this fluorescent material, it will ionize the air, causing the release of charge, more charge, and then you get flashes of light. And that's how we can detect the charged particle. Okay, so that's one way. Another way is using the Geiger-Müller tube. And how this works is as follows. So you have your high energy particle, and that ionizes the atoms, causing the release of electrons and more ions. Now, what happens is that these electrons and ions can also have lots of energy, because some of the energy is still transferred as kinetic energy. And so what happens is that these charged particles can ionize more atoms. So they can ionize more atoms, releasing more ions and more electrons, and they can ionize more atoms. So you get an avalanche effect, basically. And so you get lots of ions and lots of electrons. Okay? And so you have lots and lots of charge. If you have lots and lots of charge, how can you detect that? You can detect it as a current. So this is the Geiger-Müller tube. So we have a circuit, and we have a scalar or rate meter that basically detects a current. And then we have an anode here. So we have the power pack, so we can charge this to positive. And so the reason for that is that we can have these atoms inside. We're going to use an argon atom, okay, just for an example, because it's an inert gas, it doesn't react with anything. Okay, so we use an argon atom. Now when we fire these high energy high energy particles, some of it will hit the argon atom and cause a release of electrons and ions like we talked about. So these electrons will be attracted to the anode because it's positive and negative, and they get attracted and they move along the circuit, okay, and that creates a current. That current is detected, and so that's how we detect the presence of these high energy particles. Now last but not least, we also used another method called cloud chambers and bubble chambers. Now how this works is the same principle as when you see a plane. It has hot gases in its engine, releases them, and that vaporizes the air. But the air around it is cool, so it condenses. And when the air condenses, you see a sort of trail. You see a trail left behind by the plane. And so the idea is, if we can detect this trail that's left behind, we can basically see the trajectory of the charged particle. We can see where it went. Okay? So now even if the particle itself is not charged, what happens is you have a high energy particle, let's say you have a high energy photon, you can still ionize the other atoms, and that causes the avalanche effects that we talked about above. So eventually you'll see charged particles. Eventually there will be charged particles, okay? It can either be directly from the particle accelerator, or it can be due to the avalanche effect. Okay, so you get these charged particles that are released. Now, what happens is that these molecules around it, they're polar. So this particle is surrounded in a fluid usually, and the molecules in the fluid, they're polar. So what that means is one side is positive, one side is negative. Okay, and so it's kind of attracted. It's attracted to the ion, the charged particle. Okay, so it's attracted. Okay, and so they come close together. So if you have a gas, if you have a vapor, when a vapor comes close together, what happens? It condenses. It condenses. Think of it as this. Liquid molecules are closer together than in the gas. So the vapor condenses, and that leaves behind a trail. And so you can detect the trail, and you can detect the trajectory of the charged particle. And so if you use a magnetic field, because the particle is charged, it will bend in the magnetic field, and you can see where it went. If I use a magnetic field, I can detect the charge. I can also detect the radius. And as you can see, the radius decreases because the particle loses energy. So that's it for today. Thank you guys for watching the series on particle accelerators. Let me know what topics you would like me to cover, and see you guys next time. Goodbye.